Hello everyone, this is DA from my Academy, and today this video is about nested interval property, and we will see how to prove nested interval property. Now we'll start this with the definition of nested intervals. So if we have a sequence of intervals where there is no restriction on the interval, because an interval can be a closed interval, and it can be an open interval, and it can be half closed or half open. So there is no restriction on the intervals here. Now we have a sequence of intervals, and this sequence of interval is said to be nested intervals if I1 is a superset of I2 and I2 is a superset of I3 and so on. So we can visualize it as we have an interval I1, then I2 will be here that I1 is a superset of I2. So this interval is I1 and this interval is I2 and so on to IN, and also this is going in the same way. So I1 is a superset of I2, I2 is a superset of so on, and we have such type of intervals if we have a sequence of intervals that satisfy this property. Now we'll talk about what is meant by nested interval property. So the nested interval property states that if we have a sequence of interval, and we can write the sequence interval as IN, where every interval is a closed interval. So if IN is an interval, we have AN and BN, or the endpoints of this interval. What is n? N belongs to any natural number here. So if IN is a nested sequence of closed bounded intervals, then the claim is that there exists an element from R, or there exists a real element such that this real element belongs to IN. What is meant by this thing? That this element belongs to every possible closed bounded interval. So this is the claim, this is the nested interval property, that if we have a sequence of closed bounded intervals, then there exists a real number such that this real number belongs to every closed bounded interval. Now we are going to prove this, as it is given that we have a sequence of nested intervals and the intervals are closed and bounded. So intervals are nested. So we have that I1 is a superset of every possible interval because we have a sequence of closed and bounded nested intervals. If it is, then we can say that AN is less than B1. Why it is so? Because we have intervals like this. If it is A1, then A1 and B1, this interval is I1, and we have let this interval is IN interval. So here is AN and it is BN. So every, and this will be so on and in this sequence. So here AN is always less than or equal to B1, because B1 is the bound, it is the upper bound. We can say that it is the upper bound of all of the A1, A2, A3 and so on, because they're all AIs here. So not each one of A will exceed B1. So B1 is the upper bound of all of the AIs. So here we say that AN is less than or equal to B1, and this is also true for all n in N. We'll get here about the definition of the nested intervals. So we can say that we have a set of AIs, or AN, for all n in N, that this set is bounded above by this B1. So this set, let's call this set A. So A has an upper bound, that is B1. Now by the completeness property, if A has an upper bound, it must also have a supremum. So let zeta be the supremum of the set A. So we'll assume that because by the completeness property there must be a supremum, so we'll suppose an element of the real line, or we have a real element zeta that is the supremum of A. So now by this we can say that because this zeta is the supremum of A, that is greater than or equal to every element of an for all n, and this is the definition of being the supremum. So now in general, if we're looking at this figure, Bn is also an upper bound of this set A, because Bn is always greater than or equal to every, it is strictly greater than, or it can be possibly maybe equal to some of the AIs, but we can also say that the Bn here is also assumed to be the upper bound of all of these AIs, or all of these elements that are in A. More precisely, we can say that Bn is assumed to be the upper bound of the set A. So we can write that Bn is the upper bound of the set A. Now, looking at the other angle, if we say that n is less than or equal to k, because there are two possibilities if we're talking about the nth interval. So n can be less than k and n can be greater than k. So if it is, so we are going to talk about the two possibilities of it. So this is the case when n is less than k. So if n is less than k, we have the relation of ak, bk and bn, like ak is less than or equal to bk and bk is less than or equal to bn. Also we can say that ik, the kth interval, is a subset of the nth interval. So we have the information here that ik is a subset of in, and ak is less than or equal to bk, and this is less than or equal to bn. So this is the information that we extracted from this when n is less than or equal to k. If what happens if n is greater than or equal to k, then here this is the kth interval and this is the nth interval, because n is greater than or equal to k. So we have the relation that in, or the nth interval, is a subset of the kth interval, and the relation between ak, bn is that ak is less than or equal to an, and that is less than or equal to bn. So this is the result that was extracted when we have n is less than or equal to k, that ak is less than bk, that is less than bn, and now the result is ak is less than an is less than bn. So at both ends we have bn. None of the element exceeds that element bn. So this implies that our supposition that bn is the upper bound was correct. So bn is the upper bound of this set A, and if it is the upper bound, then what is the definition of being the upper bound, and what is the relation of the upper bound with the supremum? Is that supremum is the least of all of the upper bounds. So this is less than or equal to bn, and this is true for all n in n. Now here this is zeta is less than or equal to bn, and here an is less than or equal to zeta. So this thing implies that if we combine both of the things, this implies that zeta is less than bn and it is greater than an. So we can say that zeta belongs to nth interval, and this is true for all n in n. So we have this relation, and this is what we claimed about the nested interval property. This is what the nested interval property claimed about, that we are looking for this type of real number that belongs to every element, every nested interval. So we have proved that if we have a sequence of closed nested bounded intervals, then we are looking for, if we're looking for an element, a real element, such that this element present in every possible interval, then we can find it. So the claim was true, that is in the nested interval property. So this is for now. Looking for more such videos, and you can subscribe this channel to watch more upcoming videos. We will meet in the next video. Till then, take care. Goodbye.